I can see the screen. It's working now.
Okay, so I'm excited to present this topic because I like it. If I'm asked what is my preference to teach a topic, it would be this one. I like it. And I've applied it throughout my career a few times, applied some of the results of optimal estimation theory. Initially, I made a presentation about Kalman filter, but then it started growing to the point that where the Kalman filter came towards the end. So I think that's for the better because I want to give you the tools that would allow you to pursue this on your own if you want to get more into it. So maybe we will get to the Kalman filter, maybe not, we'll see. The layout will start with some motivating examples of estimation, then we'll cover some fundamentals in probability theory, then we will derive the linear least squares estimator, and you'll know why there's quadratic in there once we get there. And then we will derive the weighted least squares estimator. From there, I'll show you an alternative derivation of the weighted least squares as a maximum likelihood estimate, or MLE for short. And then we will cover what it means to have a recursive estimator. And eventually, if we're lucky, if you guys are not tired, we'll cover the Kalman filter. Okay, so examples. Optimal estimation helps us find the best value of an unknown parameter or variable after minimizing a cost function. Examples include, for example, if I have a resistor and I have multiple measurements using a multimeter, then I could use the results, some of what I will show you today, to estimate that resistance value. Curve fitting, linear regression, which is an important thing, and I'm sure at some point you will do it. Like, for example, estimating the coefficients of a polynomial given some sample input-output data. And linear regression also, it's done in a lot in machine learning. So it has important applications. Also, imagine we have 3 sensors on a mechanical structure. We hit with a hammer. We know the transfer function from the hammer, the input, to the sensors. Then we could reconstruct the impact loading profile. But we could use the results that I'm going to show today to estimate using all the sensors, estimate a single loading profile. Also, if we have inaccessible states in a control system that we want to estimate based on some observations, like, for example, if we have a pressure cooker and the input to this pressure cooker is the heat of the stove, and you know the pressure, but you can measure the pressure, but you would like to know the temperature inside the pressure cooker. So your observation would be the pressure, and the state that you would like to estimate would be the temperature inside that pressure cooker. Okay, so it's not a great example, but just to get you the idea, we have, for example, observing something, but it's different than what we're trying to estimate a different variable based on the observation. Estimating also location based on 3 or more GPS satellites. Also, one important aspect or use of the Kalman filter is to fuse information from different sources. So, for example, if we want to, our phones, they have something called an inertial measurement unit, or IMU, and they also have a GPS receiver. So if there's a dropout indoors in GPS location, the IMU, it integrates the acceleration twice signal from the accelerometer you get, and keeps track of the direction you're going, your orientation, and it estimates your location while GPS is while you don't have a GPS connection. Once you have GPS again, then it updates its location estimate. So this is fusing information from different sources. Like another example of fusing information, you have 2 radars measuring, like a hypothetical example, 2 radars measuring the speed of a car, and you can fuse. You want to fuse the readings, the speed readings that you get from both radars to get a single reading. Okay, let's cover some tools to help you further understand this topic, expectation. I think you've seen this before, but this is the expectation operator. The expectation of a random variable x is nothing but a weighted sum. And the weighted sum is based on a weighting function. This P of x is nothing but the probability density function. It denotes the weights that each value of this random variable takes. And then we're doing just a weighted sum to get the expected value of x. In this case, this is the mean value of x, which is x bar. And the axioms, one of the axioms of probability, that the sum of all the weights, in this case, if it's a continuous function, this p, then the sum of all weights, or the integration of all weights, must be 1. So if we have a function of a random variable x, and we want to see the expected value of that expression, g of x, then all we have to do is just plug that into this integral and weight it according to the PDF, the probability density function. What if we have an expression of 2 random variables and we want to know the expected value in this case? In this case, we would need something called the joint probability density function, or the joint PDF. And this is an equivalent expression to calculate the joint PDF. Notice we have to integrate over not only one variable. In this case, we have to integrate twice, over x and over y, to get the expected value. But what I'm saying here is that the probability of x and y is nothing but the probability of x given y. This is what the notation means, times the probability y. And this follows from Bayes, yes, Bayes or Bayesian statistics. Okay, so it basically says that probability of x and y equals the probability of x given y times probability y. And this equivalently can be stated as the probability of y given x times probability of x. My handwriting is beautiful. So yeah, so that's what it is. If x and y are independent, then that means that their joint PDF can be separated into separate PDFs, one for x and one for y. And in this case, in case that x and y are independent, and we want to know the expected value of some expression that involves so like 2 functions, one of x, g of x, and h of y, then all we have to do is separate the corresponding the expectation of the corresponding functions g and h. This is only because x and y are independent. The expectation operator is an integral. It's a linear operator. So it satisfies superposition, scaling and superposition properties. For example, if you have this expression where alpha and beta are constants, then it's equivalent to alpha times the expected value of x plus beta times the expected value of x squared. Marginal PDFs. Marginal PDF is something you would get from a joint PDF. So if we have a joint PDF, x and y, and we integrate over y, then we get the marginal PDF, or the PDF of x. If we have a joint PDF of more than 2 random variables, in this case, if we have x, y, and z are random variables, then in order to get the PDF of x, we have to integrate twice, one over y, and then and again we have to integrate over z and over y, and the order of integration doesn't matter. Mm-hmm. Yes, exactly. Yeah. Yeah, so it's not px given y, px given y times probability of y. So you just use Bayes' rule here if you want. I'm not sure if that answers your question. To y. Yeah. So if you integrate with respect to y, it means you're replacing y with fixed values, and you're doing this summing over all possible values of y. So this ends up a function of x. Yeah. So here we're doing the same, except we have 3 variables in this function. So we have to integrate over z and y to eventually have the PDF of x. Mhm. Bayes' rule. So Bayes, yeah, you can say it in different ways. So it depends how you're gonna say it. You could say, okay, this, if you want to use Bayes' rule, you can say this is the probability of, it depends what you want to do. Let's probability of x given y and z times probability of y and z. And then you could say, oh, well, the probability of y and z is probability of y given z times the probability of z. I mean, but now just forget that. This is, I'm talking about the joint PDF, just the joint PDF. You can express that in different ways using Bayes' rule. Okay, so conditional independence. Conditional independence is slightly different than the notion of independence. Conditional independence, 2 random variables, x and y, x here and y, sorry. I wrote over it. 2 random variables, x and y, are said to be conditionally independent given a 3rd random variable, z. Okay, but when we say given, so we know exactly what is the value of z. So here, what it means to be conditionally independent, we can state this formally in 2 ways. The first way is that probability x given y and z equals the probability of x and z. What does that mean? It means given information about z and y, we can, if we want the probability of x, this is the same as getting the probability of x given only z. So y, exactly. So y is redundant. Given z, y does not provide any additional information about the probability of x. So that's the probability. So that means that x and y are conditionally independent given z. And conditional independence could be stated alternatively like this. Probability of x and y given z, we can separate now. Instead of having this joint PDF, they separate as the probability of x given z, probability of y given z. Okay, this is something that you probably know, but now we're using the expectation operator. The variance of some scalar random variable is nothing but the expected value of x minus x bar. And here x bar is the expected value of x. It's the mean squared. So that's the variance. In general now, let's talk about vector random variables x and y. If we have a vector random variable, here we have 2 of them, x and y, then we will define something called the covariance matrix, and it's defined as the expected value x minus x bar minus y bar transpose. We also define an important quantity called the correlation, and it's related to covariance, and I will show you how. The correlation is the same expression, except we're not subtracting the means of these corresponding random vectors. If y is a scalar, then the covariance is nothing but the variance. The covariance of y with itself, also known as the autocovariance, is nothing but the variance. That's in the case that y is scalar. So it's a vector, an n by 1 vector. Could be, I'm saying you have a vector, and each element in that vector is a random variable. It could take a bunch of variables, a bunch of values, sorry. That's what I'm saying. I'm not talking about a random process. So a random process is that maybe you have a random vector, but now you get not one vector, you get a bunch of these vectors or samples with time. Yeah. Yeah, with time. Yeah. So that's called a random process. Yeah. Yeah. Yes, yes. So here, this is you reminded me. Here, when I say vector, I explicitly say column vectors. Because in certain statistics books, they use row vectors. So that you might see the expectation will be x minus x bar. The covariance, for example, of x and y would be x minus x bar transpose. But no, here we're yes, exactly, it's a matrix. And this is a symmetric matrix. This is a symmetric matrix, and yeah, for now, it's a symmetric matrix. Yeah. So the covariance is not a function. The covariance, we calculate the expected value. So you get, yes, you get numbers. Yeah. So for example, in the autocovariance case, the diagonal elements are going to be the element-wise variances. So, or the variances of each element in Y. And the off-diagonal elements are going to be the correlation between the different elements in the Y vector. And this is the relationship between the covariance and correlation. And so basically covariance of X and Y is the correlation of X and Y minus X bar, Y bar transpose. And you can actually show this, you can get to this expression easily if you start from the definition of the covariance. This is, let me see, I need to write small. So this is the expected, let's expand this expression. So it's the expected value of X, Y transpose minus X, Y bar transpose minus X bar, Y transpose plus X bar, Y bar transpose. But wait a minute, the expectation operator is a linear operator. So we could just take the expectation of these individual components and then sum them together. Like take the expectation of this minus the expectation of this minus the expectation of this plus the expectation of this. What is it called? Sure. Yeah. Also, one important thing to note here is what is the expected value of, for example, this term. So we have, no, this is the expected value of the first term is the expected value of X, Y transpose. So this is actually the correlation by definition, okay? But then what is the expected value of X, Y bar transpose? But this is Y bar now. We have Y bar. So Yes. So y bar is just a constant. Y bar is just a constant. So remember, a constant and expectation is an integral. So we take that out of the integration. So then we have correlation minus exactly expected value of x scaled by, and you have to write it like this because you need to keep the order. Y bar, sorry. But what is the expected value of x? It's x bar. So we have minus x bar y bar, and here we have plus x bar y bar. So this term cancels with this term, and you end up with this term. You follow the same logic, you get to this expression. Two random variables are said to be uncorrelated, and this is something that I don't like because two random variables are uncorrelated if their covariance is 0. Okay, but so and also two independent random variables. If I tell you that x or y are independent, then that implies that they are uncorrelated. Their covariance is 0. However, the converse is not true. If I tell you that two random variables are uncorrelated, then you cannot say that they're independent. You cannot conclude that they're independent. Okay, this is also something that might be handy, this relationship in the upcoming slides. If we have a sum of two random variables, x and y, I want to find their covariance. Then if you go through the definition, you take the expected value of this sum, then you end up with this expression on the right-hand side. So the covariance of the sum of two random variables is nothing but the autocovariance of x and autocovariance of y, covariance of y with itself, x with itself, and the cross covariance x and y plus the cross covariance of y and x. But the cross covariance of y and x is nothing but the cross covariance of x and y transpose. So this is a matrix, and this is the same matrix transpose. Okay. So if x and y are uncorrelated, then we get rid of the last two terms here. If x and y are uncorrelated. Also, one important thing to know is the definition of an unbiased estimator. Have you heard of? Okay. An estimator, let's say we want to estimate a variable x, a random variable, and we come up with an estimate, and we call our estimate x hat. Then our estimate is unbiased if the expected value of x minus x bar is 0. What does this mean in words? It means on average, the estimation error, which is x minus x bar, is 0, which is a nice property. It is a desirable property to have in an estimator. Linear transformation. Say we have a random variable x. Now here, x is a random variable and h is some deterministic matrix. It's not stochastic. So what can we say about the average or the mean of y and the covariance of y under this linear transformation? I mean, if you just go through the definition, if you say y bar is the expected value of y, and then this is a constant, it comes out of the expectation. So this is h x bar. Okay. And the covariance, if you go through the, because the covariance is going to be the expected value of y transpose, right? And this is the expected value of y is nothing but hx, so hx transpose. This is hx x transpose. Oh, no. Yeah, no. Transpose H transpose. Yeah. So this is a constant, comes out of the expectation. This is a constant, comes out of the expectation operator. You end up with H covariance X, autocovariance of X times H transpose. So again, these are handy when we get to the Kalman filter or recursive estimator. It is the autocovariance. Yeah, so also known, I said also known. So the covariance of a vector with itself is the autocovariance. Yeah. X, because I said X is some unknown, is a stochastic variable, and it's n by 1. So it's n by 1, over here, it's n by 1 times 1 by n. So it's n by n. Yeah. No problem. Okay. So the next thing now, let's assume that we have an additional random variable that we sum to hx. And let's assume for now that this random variable v and x are uncorrelated. Then what can we say? And that v is 0 mean. Then the covariance of y, remember now the sum relationship. When you sum two random variables, we're summing this random variable to this random variable. So the covariance of y in this case, the sum of these two random variables, is nothing but the autocovariances plus the cross covariance. But the cross covariance, in this case, I'm telling you, x and v are independent. So it's going to be 0. So eventually we know that this is going to be the covariance, the autocovariance of hx, and then we have the covariance of the noise, the autocovariance of v. Okay, this is now for this slide and the next one, I'm not going to spend a long time, but I'm going to give you the slides at the end. What happens if you have y, which is an m by 1 vector that equals a is an m by n matrix times x is a vector, an n by 1 vector. What happens if I tell you I want to find the derivative of y with respect to x? What is the answer for that? Well, basically you tell me, let's define that. What do you mean by the derivative of y with respect to x? Well, this is called the Jacobian matrix. And you just take each element of y, you differentiate it by x1, and then you differentiate it by x2 until the last element of x. And then you go with the second element of y until the final element of y. You just take all the derivatives of all the elements in y with respect to all the elements of x. So if we follow this definition, it can be shown, and I show you here step by step how to do it, that the derivative of y with respect to x is nothing but a. It's similar like, what if you have a t and you differentiate that with respect to time? You get a. So this is similar, but I mean, it's not straightforward. It's not to be assumed you have to prove these things. So this is, you can find, I'm sure you can find references about that only, but this result and similar results are going to be useful if we have a multivariate quadratic function, for example, and we want to differentiate that expression. Okay, so this is something also that you might have done or you might have seen before, but the way I derived it, maybe it's the first time you see it. It's the pseudo-inverse. We'll get eventually to the pseudo-inverse, but we'll show you the steps how to get that expression for the pseudo-inverse. So let's go back to our problem. we have, but this is, no, this is, I need to explain this. So assume we have some measurements or observations, and this model is our measurement model. And these measurements are noisy. They're corrupted by this zero mean noise vector. And let's assume here that H is a known matrix, M by N matrix, and measurements are M by 1. And let's assume that we have at least as many measurements as parameters in X, which are the ones we would like to estimate. So we want to estimate X from M measurements, and M is at least as large as N. Okay? And it makes sense. We have more measurements than parameters we want to estimate. So notice that there is the linear relationship. If you ignore the noise, there's a linear relationship, obviously, between Y and X. And we can define our optimal estimate, X hat. Now, I already said it. For optimal estimation, we need to define a cost function. So our cost function in this case, we want our estimate is the argument that minimizes our cost function. This is our cost function. The cost function is going to be our, let's see, y minus expected value of y. Expected value of y, remember here, this is the expected value of v is 0. So the expected value of y is nothing but hx. All right? So eventually, so what I'm saying is that this is the noise term, and we don't know what it is. We know what y is. We know what h is. Okay? We can subtract y. You can subtract hx from y. We get y minus hx. And this will be our error vector. So we're trying to minimize our error vector. So we use that to define our error vector. I call it here epsilon sub y vector. This is just the inner product of the error vector with itself. It eventually ends up being the squares of the elements in that error vector. And each element is weighted the same with a weight of 1. Okay? So if you expand this expression, you have y transpose y. This is a linear term in X. This is a linear term in X. By the way, this term is exactly the same as this term. It's nothing but, it's like having two vectors. Let me call them Z1 and Z2. The inner or the dot product of Z1 and Z2 is going to be the same as the dot product between Z2 and Z1. So it's like saying the dot product here is Z1 transpose Z2 equals Z2 transpose Z1. This is like a dot product operation, okay? So these are exactly the same terms, the same term. And here, this is a quadratic form. This is called a quadratic form. Long story short, our objective function is quadratic in X. And here, it's not only any quadratic, it's a quadratic function that is concave up, like this, also known as convex function. But this is like a simplification if we imagine that our objective function is a function of a scalar variable. Okay? Okay, this is a big deal. Because we guarantee a minimum and not a local minimum. That will be the only minimum we have, the global minimum. So we now differentiate with respect to X using matrix differentiation rules, and I showed you an example of them. Let's see. And then we set to 0, and there we go. We have our estimate. So this is our objective function. We expand it. Now we take the derivative with respect to X. That's and we set it to 0. This is the derivative. Notice here, remember a times X. And when we differentiate with respect to X, we get A. This is the same. Now, if you differentiate this term, the quadratic form, actually quadratic form, if you have x transpose ax, and you take the derivative with respect to x, this expression, you get a plus a transpose times x, which is the same as x transpose a plus a transpose. If a equals a transpose, then you get, for example, x transpose 2 times x transpose times a. So this is the same thing, 2 times x transpose times this matrix, which happens to be a transpose H, is a symmetric matrix. Okay. Then we just solve for x. This simple algebraic equation, solve for x, and then we get our expression of our estimator. Notice that the expression for our estimator involves known quantities, the H matrix, which we already know, and Y is the measurements that we already have, its numbers. So we can crunch these numbers, and this is called the pseudo-inverse, specifically the left pseudo-inverse, because if you multiply H from the left with the pseudo-inverse, you get the identity. So that's why it's called the left pseudo-inverse. So now, as an exercise, I'm not going to do it here. Show that if this estimator is this estimator, or this x hat is unbiased if the noise v is indeed zero mean, but it will be biased if the noise is not zero mean. This is why it's a good idea, at least in my work, I use a high pass filter to make sure that my acceleration signal, when I do my analysis, is zero mean before because there's a slight bias, yeah, or detrend, yeah. So now we covered the least squares. Let's see what a weighted least squares would be. It's going to be similar, the same steps with a slight difference. The only difference here is that not only we'll assume that the noise is zero mean, we'll assume that we know its covariance matrix. And the covariance matrix will assume it's a diagonal matrix. So this is a diagonal matrix like this, sigma 1 squared, sigma 2 squared, blah, blah, blah. Okay. So we think of Y as M sensors. And each sensor might not, the sensors might not have the same noise level, because sigma squared is nothing but the noise power in your signal. It's the mean squares, literally. If you calculate the mean squares in the acceleration signal, you get an estimate of your sigmas for each sensor. So you might have a noisy sensor, or that has more noise than other sensors. So you want to put less weight on the measurements that's coming from that sensor. That's the idea behind the weighted least squares estimation. So in this case, our optimal estimate is we want to minimize not only the mean squares, the squares of the error vector that we've introduced earlier. We want to, each element in that error vector, we want to scale it by dividing it by sigma squared. So if you have a noisy sensor, that means it will have, compared to the other sensors, it will have higher variance compared to the other sensors. And since you're dividing by this, 1 divided by that higher number is a smaller number. So it's like you're multiplying that corresponding element in the error vector with a small factor, because you're basically saying, okay, here's my objective function, and I want to put less weight on the error that is coming from that specific noisy sensor. So if you want to express this in matrix form, it looks like this. Because we're dividing by sigma squared, it makes sense we're taking the inverse of our covariance matrix R. So now we want to minimize this function. So previously in the linear least squares, we did not have this. That was identity. All the errors were weighted the same. But here we have a weighting using this matrix, a different weighting. Same procedure. This is going to be quadratic function, which is convex and nice, and we can find the global and only minimum by differentiating and setting the derivative to 0. And then we get this expression. And you can compare it and see the difference. It's basically if you replace R with identity, then you get the least squares or LLS estimate that we showed earlier. But this is the expression now for the weighted least squares. And similarly, you can show that this is indeed an unbiased estimate if the noise V has 0 mean. The extra information you need is the noise level, the noise floor of your sensors. Yeah, but that's yeah, which is electronic noise. That's like putting maybe the sensor in a chamber, isolated, and then measuring that noise floor. You have two sources of uncertainty. Your measurement model that you assume is linear might not be perfectly linear. So you have that source. And you have also in the specific example of a structure and accelerometers on it, you might have maybe a fan moving that's adding noise or someone walking nearby. So that's going to also appear in that signal. I want to show you an alternative derivation. And after that, we'll see if you want to proceed further or go, or maybe finish in next week. So I'm going to give you how to get the same result, how to get to the weighted least squares estimator, but in a different framework, which is the maximum likelihood framework. Let's see how that works. So same everything as before. We have this 0 mean noise vector. We know the covariance of it. But now, not only that, I'm going to tell you that this noise is Gaussian or normally distributed. So it's a normal distributed additive noise, 0 mean, covariance matrix is known. And again here, we want to assume that the covariance matrix is some diagonal matrix. Now, this looks like a scary expression. It's just the expression for a normal or Gaussian distribution, Gaussian PDF, but this is the multivariate version. So notice what's inside the exponential argument. This is what, a vector or a scalar? A scalar. This is a quadratic form. It's some, the V is m by 1, but here we're talking V transpose. So this is 1 by m, and this is m by m, and this is m by 1. So it's a scalar. So we're crunching everything into one number. All what we're doing, we're finding, we're subtracting the mean from V, and then we're getting like a weighted norm. It's a norm of, we're calculating the norm of V, but we're weighting it by the covariance matrix, the inverse of the covariance matrix. And DET here is the determinant of R, the covariance. So the covariance is a matrix. This is the determinant of that matrix. One, I guess now something that came to my mind. If you have a vector, let's call it Z, and it's n by 1, for example, or m by 1. And then you find a matrix, and Z is just constants, right? And you have a matrix, you calculate, it's a real vector. you calculate Z transpose, Z transpose. And then you get this matrix. And then you calculate the determinant of Z transpose. What do you think the answer would be? It says singular. It's going to be 0. Yeah, it's built in one. It's the outer product. It's just one vector, literally having the same vector, stacking it in a matrix, but in each column, we're multiplying it by a different constant. So it's rank deficient. So if it's rank deficient, then the determinant is 0. It's not a full rank matrix. But but it's a different story when you put the expectation value. So when we calculate the expectation, you might see, oh, the R is nothing but the expected value of V transpose. But this is different. This will be a matrix that we can invert. Okay. So that's why here we can invert that matrix. And in this case, the matrix is just a diagonal matrix. So just food for thought. No, I'm saying just the form, because the outer product V transpose, you might get the impression that but no, we're taking the expected value of a random variable. Okay. The measurement model HX plus the noise means that the PDF, meaning that the probability of Y given X will also be normal. Can you find, so if you look at this model, we know that this guy is normal with 0 mean and covariance matrix R. Then can you, given this information, if I give you the value of X, given X, can you tell me what will be the distribution of Y? I already told you it's going to be Gaussian. Because this is Gaussian, right? And if I give you X, if X is known, then this is just a constant. So it's just like having a constant in addition to a random variable. So it's going to be Gaussian, but shifted. The mean would be shifted. The Y would be a Gaussian distribution, but the mean of this distribution will differ from the mean from this distribution by this much. So, okay, that's for the mean of this PDF, Y given X. But what would be the covariance of Y? Or what would be the covariance matrix of Y? Which is, this should come right in here. Again, this is Y given X. So if I tell you I have a deterministic quantity, and I tell you, give me the covariance, not that. If I tell you, I know that this pen has a length of exactly 10 centimeters. And then I tell you, what is the variance on its length? Tell me, its length is known. Its variance is 0. We know exactly what it is. So here's the same thing. I'm giving you X. H is also known. So this term is a constant. So its covariance, or its autocovariance, is going to be 0. So you're left with remember, this is the sum of two random variables, except now Y is the sum of two variables, Hx and V. This is deterministic, and this is stochastic. So eventually, then the conclusion is it's going to be a normal distribution with this mean, Hx, and the covariance of the noise. But that's Y given X, the PDF of Y given X. Okay, let's plug that in the expression for the multivariate normal PDF that we just showed you in the previous slide. So this is the mean. We plug it here in the mean. and this is the covariance. We take its inverse, plug it here, take its determinant in the denominator. This is our expression for the Gaussian distribution in this case. Now, f of y given x is called the likelihood function. Okay, and given the measurement vector, now we're twisting things a little bit. Say now you are given y, but you don't know what x is. But you have this expression. So one estimate of x, I'm going to call it x hat, is the parameters that maximizes the likelihood of seeing the observations y. Okay, so that's the maximum likelihood estimate. Let's look at x. Where is x? X appears in the mean. So x is some function of the mean of this Gaussian distribution. It's a parameter there that I don't know what it is. But what if I tell you, okay, I'm going to give you the values of y. I'm going to give you the values of y, but now x is unknown. So one way of getting a value of x is we want to find the value of x that makes this function the maximum, as high as possible. Basically, based on the observations, this is the parameter that makes sense. That is most likely to be the right parameter that should be used in the PDF. So that's the maximum likelihood estimate. So now here, pay attention. Y is given. I want to stress this again. Y is given. So once you substitute the value of y, then you have a function of x, really. This is the likelihood function. And that function of x, as a function of x, is not Gaussian anymore. The function here that is Gaussian, it's a function of y. But now once we plug in y and we don't know x, so it's a function of x, and that's the likelihood function. So actually, if y given x is called the likelihood function, I want to say here, well, it's basically given y, but now we want to estimate x. So the argument that maximizes the likelihood function, the parameters that maximizes the likelihood function, are equivalent to the maximizing. So maximizing f of y given x is equivalent to maximizing the log likelihood. And this comes from optimization theory. So taking the log of a positive function, the log is a monotonously increasing function. So you can say the statement because the log is monotonously increasing. So it doesn't go up and down, it keeps going up. Okay. So you can do that. Now, maximizing a function is equivalent to minimizing the negative of that function. So now we want to find the argument that minimizes now the negative of the log likelihood. And this is equivalent to, if you take the log of this exponential, then you get to the inside argument. But these are constants. This is a constant. This is a constant. So we want to minimize only the numerator. Skip. So yeah. So have we seen this before? Does this look familiar? This is exactly the minimization problem we dealt with when we derived the weighted least squares estimate. Okay, so we have the likelihood function, and now I'm throwing another jargon here. The maximum a posteriori estimate, MAP. We established that this is known. This is our measurement model, really. Hx plus v, if x is known, we know the PDF, and we have a Gaussian noise. So we know the PDF of this, and we called it the likelihood function. If we are willing now to treat x as a random variable rather than a constant. So far, we treated x as an unknown parameter, an unknown constant. and we want to estimate that constant. But now let's say, okay, let's treat x itself as a random variable that can take different values. And if we also know the distribution of x, that is the PDF, f of x, the probability, the different values of x appear, then using Bayes' rule, the probability of x given y equals the probability of y given x times the probability of x divided by the probability of y. Remember what we said, what I said about Bayes' rule in the beginning? I said f of xy equals the probability of x given y, probability of y, and you have same as probability of y given x, probability of x. So you use that fact to come up with this expression. But wait a minute, if we know this, this is the likelihood function, we have a measurement model. And if we know this, I'm assuming that we know this distribution. By the way, this distribution, I'm going to call it the prior distribution, because it's distribution that I know prior to seeing the observations y. After seeing the observations y, I can use this expression to get the posterior distribution. So y is given, remember, y is known. So it's like saying, and I'll talk about the denominator in a minute, but it's like saying, what is the probability that you would pass an exam? Let's say it's a comprehensive exam or placement exam. It's a 50-50 chance. Okay, but then that's our prior distribution. But then I tell you, oh, but what is the probability that you would pass that exam given that you did not study? Oh, wait a minute. Now you have additional information. So if we want to incorporate this additional information, we get the posterior distribution, which is the probability that you pass an exam given that you did not study is most probably it's going to be less than 50%. Okay. So this is what we're trying to do. We have a prior distribution, but then we have additional information, some observations, and we want to use that observations to get a revised distribution. So that's this distribution here is called the posterior distribution of x given the observations y. And now this is called the prior distribution. We know the likelihood function in green, and we know, I assume that we know the prior distribution, but what is the denominator here? If we know what y is, and I tell you what is the probability of y being a certain number, you just look at the PDF and you can tell me you're going to give me a number between 0 and 1. It's just a constant. It is just a constant. So that constant, you can find it using the marginal, you can marginalize over the joint PDF. Remember, the joint PDF, f of x and y, is nothing but f of y given x, this is the likelihood function we already know, times the prior distribution that we already know. Okay, so this is the joint PDF, so we marginalize over that joint PDF, we integrate over x, and then we get the PDF of y alone. We already know, so on the right-hand side, we have knowledge of all what we need to calculate the left-hand side. So previously, we found x that maximizes the observations, the likelihood of seeing the observations. We call that the MLE estimate, or maximum likelihood estimate. Now, what if I tell you I want to maximize this posterior distribution, because it's the one that incorporates additional information about the observation? How can we, so now let's define our maximum a posteriori estimate as the argument that maximizes the posterior distribution. This is equivalent to the argument that maximizes the numerator here, because again, the denominator is a constant. Okay, So this is just to tell you what maximum or the map estimate is. And the map estimate is actually what the Kalman filter does. So you get a bunch of measurements, and as you get, so you have your initial belief about your parameters, and then you get a measurement, and then you update your estimate based on the observation that, and you keep doing that in an iterative manner. One important thing to notice: if this prior distribution is Gaussian and this likelihood distribution is Gaussian, then if you multiply a Gaussian distribution by another Gaussian, the result is going to be Gaussian. And this is one of the interesting things about Kalman filter. It does this thing. It fuses information by multiplying PDFs. And these PDFs happen to be Gaussian. So all what you need to know about the Gaussian distribution to describe the Gaussian distribution is its mean and variance. And this will come up later. Now, another thing about fusing information, maybe that's interesting to know. Going back to the radar example, if you have two radar devices and the officer is holding them next to each other and is observing the speed, the measurement of each one of this radar. So now we have two measurements. Can we fuse them together and get a single estimate of the speed of the car? Well, we can do it in this framework. Let's talk about the likelihood. Let's say I have this is the first radar measurement model given the speed of the car, and this is the measurement model that I already know from the first radar. So I know this. And the second radar is giving me Y2, I'm going to call it, another measurement given the speed, the same X of the car. But what I am after here, let's say we want to find the best estimate using the maximum likelihood framework. So the maximum likelihood framework, first we need to come up with the likelihood function and then maximize that likelihood function. So the likelihood function in this case is f of y1, y2 given x. You can think of it as a joint likelihood function between y1 and y2. Now we invoke something that we covered in the previous slides. What does it mean if I tell you that y1 and y2 are conditionally independent given x? Then it's going to be y1 given x, y2 given x. And imagine so of course, if this is Gaussian normal distribution, and this is another normal distribution, probably different here, different mean and variance, covariance, and here different mean and covariance. And then you multiply them together, you get another Gaussian distribution. You take the log likelihood, it becomes, and then that's your objective function. It's a nice quadratic function. You take the derivative, set it to 0, find your optimal maximum likelihood estimate. Okay. Now, if you have the prior distribution, you can find the map estimate. But now, we already talked about how to find the map estimate from the likelihood function. I wanted you to just get an idea, a feel of what it means to fuse information from two systems. This is system 1 and this is system 2. I want to fuse these information because we know the PDF, F is the PDF of y1 given x, the first system, and the second function gives us the PDF of the second measurement coming from the second radar. We just multiply them by each other, assuming, of course, conditional independence. So we've covered linear least squares, weighted least squares, maximum likelihood estimation, and map estimation. Showed you Bayes rule, covered some basics. I think that's good enough. Yeah. I think that's good enough. So this, you have all the tools now, I think, to tackle Kalman filter, not with hand waving and not understanding what the equations mean. Now you can make sense of the equations, and hopefully it'll stick better in your minds. Go ahead, Dr. T. Yeah. So it's like having measurements from an accelerometer, and you know that you have some signal, true signal, that's coming from the excitation. Plus, you have some noise, but not, then you need. So what you usually do, you make an assumption that your noise is Gaussian because it's easier. It makes the problem more tractable. Yes. So in the development we've done so far, we assumed that that in this measurement model, that the noise is zero mean and has a covariance R. But we could assume that it will have covariance R sub K. What does that mean? At each instant of time, you give yourself the liberty to change that. Okay, but if you're if you want to have a time varying covariance, you could do that. But here, let's get to the recursive estimation, then that becomes clear. Okay, so we'll stop here. So sorry, usually in a like a formal course, maybe you cover this in a slower pace. Stop share and stop recording.